Okay, so sorry for the cut, but my computer has done updates. Okay, so I wasn't able to use it for half an hour. So let's continue with what I have done previously. Okay, so let's share my screen. Okay, so I have finished my little previous introduction saying that when I want to compute the Greeks using combining finite difference scale and Monte Carlo methods, okay, I have a dilemma. When I reduce one error in general, okay, I increase the other. And as we have seen in the first session, okay, an ID is to express the Greeks, so here at time t equal to 0, as, okay, the expectation of the payoff multiplied by a random variable that I call a weight, okay, in order to avoid finite difference scale, okay, and the idea is to have the same source of error as the one I have computing prices, that is the one coming from Monte Carlo methods. Okay. So I remind you that in previous sessions, okay, we have seen using basic tools, okay, that for the Black-Scholes model, that is the case where sigma and b are given by this expression. Keep in mind that here I have small r because I suppose that my dynamic is under an equivalent Martingale measure. Okay, and for a payoff of this form here, I have obtained for the delta and the gamma at time t equal to 0, these weights allowing to use only Monte Carlo methods in order to approximate them, okay, without using finite difference scale. And the idea of the today course, okay, is to be able to obtain such weights here for both different models than the Black-Scholes one. So I want formula that extend in some sense this one, and also for other situation there, this contingent claim here. Okay, so we are going to do the job today for this kind of contingent claim, but also for Asian type ones. Okay, so it's what we are going to do now. Okay, so keep in mind that the dynamic of my risky asset is given by the equation E, that is what happened, okay, under an equivalent Martingale measure Q. I suppose this condition in order to ensure the existence and the unity of this solution in the strong sense, and in particular you have here that B and sigma that are Lipschitz in the second variable. Okay, it's exactly the meaning of this one. They are Lipschitz, okay, for fixed t, they are Lipschitz in the second variable. We are going to add two extra conditions, okay, in order to be able to deal with, okay, what I have done previously in the course. So I add two extra conditions. We are going to suppose that B and sigma are in fact C1. A priori, in my classical condition, I have only the continuity of B and sigma in the second variable because they are Lipschitz. I impose them to be of class C1. It's exactly what happened in the Black-Scholes model, because in the Black-Scholes model, B and sigma are linear in X. Okay? And I will denote from now on B prime and sigma prime the derivative with respect to X. Okay, so when I will denote by B, when I will use B prime and sigma prime, I will mean the derivative of this mapping with respect to the second variable, and the derivative of this one here with respect to the second variable, this one with respect to the second variable. And I also suppose that there exists an epsilon such that the volatility coefficient is strictly greater than epsilon. Okay, it's what I call the uniform ellipticity, uniform ellipticity condition. And you will see that, okay, where I will use it later on. Okay, so keep in mind that under the classical condition, B and sigma are Lipschitz, and if I use this one, they are C1. So if I have the two, I am C1 and Lipschitz. And keep in mind that C1 and Lipschitz was exactly the condition to have in order to be able to apply the chain rule for the Malliavin derivative operator. And that's why I imposed this condition here, because I want to use the chain rule in what I will compute later on, okay? And I will need that my mapping are C1 and Lipschitz. Okay, so now we are going to explore the link between the derivative operator in the Malliavin sense, okay, and the solutions of my stochastic differential equation. So what we are going to see just after is that if I am under all these conditions here, the condition of slide 6, then for any fixed t, okay, x capital T, the x small t, that is the value of my solution at time t, will belongs to the domain of the derivative operator, and I will be able to compute explicitly what is the value of the Malliavin derivative operator for capital X small. But before to do this, okay, I need to do a little reminder, okay, in relation with what you have done during the previous semester. That is this one. Okay, so maybe I will reduce a little this slide here. So I have my stochastic differential equation. So I have x0 small x that is given by small x. It's my initial condition. And I have the stochastic differential equation that I have supposed for small x. So something that I have already said is that under the condition C, I have reminded to you that this mapping is continuous for mu almost W. So I have the continuity of my solution at time t with respect to the initial condition under the classical conditions, ensuring the existence and the unicity of a solution to my stochastic differential equation. Okay? So now keep in mind that I have C plus my two extra conditions. And I have this lemma that I have called lemma 4 that tell me the following. If I have my condition C, and if I add my two extra conditions, then I can say a little bit more concerning the regularity of this mapping. So under these conditions, if I study the regularity of the dependence of the solution at time t with respect to the initial condition, then this mapping is C1 for mu almost W. Okay, so it means that I can compute its derivative, okay, and that its derivative is continuous in the initial condition. So I can define in this way, I will define what I will call the yt of x, that is the first variation process. That is defined this way. Yt of x is just the derivative of this mapping with respect to my initial condition, that is d of xt of x over dx. Okay, so I have this one. The first thing I can remark is that y0x is equal to what? So it's the derivative of this one with respect to small x. So the derivative of x0x with respect to small x, that is equal to 1. Yeah, I have this one. And what is more, I can prove that the first variation process fulfills, okay, a stochastic differential equation. That is, okay, yt fulfills this stochastic differential equation that is related to the previous one, that is the one fulfilled by capital X. So this result is not that complicated to prove, okay, but I want to do it, okay, because it's a kind of prerequisite, okay, concerning results from the first semester. But just to show you what happened, okay, so suppose that you have this equation, okay, this equation. If you compute the derivative with respect to x concerning this equation, okay, and suppose that you have the right to do this, okay, brutally, okay, then what I will obtain? So if I compute the derivative of this term, I will have d of y. If I compute the derivative of this term, I will have what? By the chain rule, b prime at the point t x t x multiplied by the derivative of x with respect to small x, that is exactly y. Okay, so that's why I will have b prime multiplied by y here, okay, and plus the same for the sigma. So it means that this stochastic differential equation here is obtained differentiating with respect to x, this one, okay? So I can write it this way to be, so I have this. If I have my stochastic differential equation here, if I compute so the derivative with respect to x, I obtain what? I obtain dytx equal to b prime, that is the derivative with respect to the second variable t x t x y t x dt plus sigma prime using the chain rule once again. This one multiplied by the derivative of x with respect to small x, it's what I have called y dv. And of course, okay, to be clear with the proof of this lemma, okay, what I have to justify is the fact that I have the right to compute this derivative this way, okay, that I have the right to do naively what I have done here, okay. So I won't do this proof now, okay, but the idea is this one. So it's what we call the first variation process, okay. That is, I repeat, the derivative of my solution with respect to the initial condition. And I know that it is possible to do this because I have supposed the set of conditions capital C that are the one that ensure the existence and the unicity of the solution, and that ensure the fact that my solution is continuous in its initial condition, plus my two extra conditions that allow me, okay, to have more regularity concerning the dependence of the solution with respect to the initial condition. So I see that here, y follows, okay, the new stochastic differential equation, okay, where my coefficient here, b prime and sigma prime, are bounded, okay, because it's the derivative with respect to the second variable. So it means that I fulfill here the set of conditions C in order to ensure the existence of the unicity of this solution. And what is more, as a solution of, let's say, a good stochastic differential equation with the good, okay, hypothesis, I obtain that my y, the first variation process, is a process belonging to this set here. I can put an x here to be clear. It belongs to L2 prog of omega times 0 capital T. And here, okay, I see that the form of this equation, applying Ito formula to the logarithm of ytx, okay, give me this form for yt. So it's exactly the same trick that you use, okay, when you obtain the form of the solution in the Black-Scholes stochastic differential equation, okay, so you have exactly this. Or conversely, you can also check that if I write yt this way, if you apply the Ito formula to the exponential of this process, okay, you recover exactly this stochastic differential equation, okay? So in particular, I have that the first variation process is always strictly positive. Okay, this first variation process is always strictly positive. Okay? So keep in mind that if I am in the case of the Black-Scholes model, in the case of the Black-Scholes model, I know that xt of small x is given by x exponential. So I am under Q, so it is R minus sigma square over 2 t plus sigma bt. And here I see clearly, without using any type of theorem, that the dependence of the solution in small x, okay, is of course C1, it is of class C infinity. And when I compute the first variation process, that is the derivative of this one with respect to small x, I just obtain the exponential here, and so I can obtain that in the case of the Black-Scholes model, the first variation process is simply the process itself when I have made disappear small x, that is when I have divided by small x. Okay? So the first variation process is given by this definition and follows the stochastic differential equation in. And in this way, using this first variation process that is related to the dependence on my solution with the initial condition, we are going to be able to set the following result that tell me that under the set of the previous conditions on the coefficients of the equation capital E, for any t belonging to 0 capital T, x small t of small x belongs to the domain of the derivative operator, okay, the derivative operator in the Malliavin sense. And what is more, I am able to compute this derivative operator, and I see that in the form of this derivative operator, okay, I obtain something that depends on the first variation process, and that's why I have used it here. This. Okay. So let's have a look on this result here. So I have to prove two things. First, that I am in the domain, and then that I can compute the derivative in the Malliavin sense this way. Okay. So for the point one, okay, I will admit it today, because it is a little bit technical. But it will be the objective of one of the projects that I will give to you, okay, as an evaluation of this course. Just have a look on, okay, what I have to do in order to prove that xt of small x belongs to D. In fact, I have two ways to prove this kind of result. The first way is to come back to the proof you have done with Mr. de Meyer concerning how to show the existence and the unicity of the solution of a stochastic differential equation under the condition capital C, calligraphic C. If you remind the proof, okay, you have used an iterating scheme, that is the classical fixed point or Picard iterating scheme, in order to prove that such a solution exists. And in fact, using this iterating scheme, okay, you can prove that each iteration belongs to the domain of the derivative operator in the Malliavin sense. And then using the closeness of this domain, okay, it would be possible for you to prove that the limit, that is none other than the solution of my stochastic differential equation, belongs to the domain of the derivative operator. Another way to do is to use as an approximation of my solution of capital E, the classical Euler scheme, okay, that is just an extension to the stochastic case of solution of ordinary differential equation. And you can prove once again that the approximation converges to the solution, that the approximation belongs to the domain of the derivative operator, and that you can compute the derivative of the approximation and prove that, okay, the derivative of the approximation will converge towards someone, and using the closeness of the derivative operator to prove that the limit is in the domain and that, okay, the value of the derivative for capital X will be obtained computing the limit of the derivative of the approximation. Okay, so for some of you, you will see this, okay, in one of the projects that I will give to you. I will focus now on the way I obtain the value for the derivative operator. So I suppose that xt small x belongs to the domain. So from small one that I have admitted, xt of small x belongs to the domain. Okay, and I know from the fact that x follows equation E that xt of small x is given by x plus the integral between 0 and t du xu x du plus the integral between 0 and t of sigma u xu of x dB. Okay, so now the first remark before to compute the derivative of this term. I have an indicator function here. I have an indicator function here. And why I have this indicator function? Because I know that xt of small x is FTB measurable. And we have seen together that when I have something that is f small t measurable, if I compute its Malliavin derivative at the point S, I obtain 0 for S strictly greater than t. So that's why, okay, from this result that is known, okay, supposing that I have this, knowing that the solution of my equation is adapted to the Brownian filtration, then the value at time S of the derivative operator in the Malliavin sense, okay, is equal to 0 for S strictly greater than t, something that I have proved, okay, at the end of the course number 4, if I remember, okay? So I have this. So that's why I have this indicator function here, okay? And so what we are going to do here, since I know that if the condition of the indicator function are not fulfilled, I have this equality, we are going to suppose that t is strictly greater than S. Because when it is not the case, I have already this equality because I have 0 in both terms here. And now we are going to be able to compute this. So I have ds of xt of small x. So that is equal to what? So here I have a constant, so it is equal to 0 plus ds, the integral between 0 and t, du xu of x du plus ds integral between 0 and t sigma of u xu of x dB. Okay, I know the following. So if I come back to what I have done previously, so it was something I have proved. Maybe it was in this course here. Okay, so so let's have a look on what I have done here. So it was not this one, excuse me. So maybe I will take maybe more this one here. So I have this proposition 6 here that ensure that under good condition I can compute the derivative of a stochastic integral or of a Riemann integral of a regular stochastic process here. And I have these conditions here. Okay, so we are going to suppose that I am under the condition of proposition 6 in order to be able to use these computational rules for my problem here. Okay, so from the proposition 6 of the course, okay, if I come back to my problem here, I am here. Excuse me. I am here or I am here. From proposition 6, I can say that here I have the derivative of a Riemann integral, so I can invert simply. Plus the derivative of the stochastic integral, and I know that this derivative is given by sigma of s xs of x plus the integral between 0 and t of ds sigma of u xu of x dB. Okay, so I have this from proposition 6. I apply the result of proposition 6 both for the Riemann integral here and the stochastic integral here. So keep in mind now that I have to compute these terms here. This term and this term. And what I know is that B and sigma are C1 and Lipschitz in the second variable. So they are C1 and Lipschitz in the second variable. So according to what we have proved together, that is not this one, excuse me, we'll prove it. So yes, I have the chain rule, okay, that I can use concerning, okay, the fact that I have a nice formula if I compound a mapping that is C1 and Lipschitz with an element in the domain. I have the classical chain rule. Here you have the multivariate chain rule, but the one I will use in my problem here is for n equal to 1. So let's come back to my point here. That is this one. Using now proposition 2, I can use the chain rule that tell me that the integral between 0 and t of what? So it is b prime of u xu of x ds of xu of x du plus sigma s xs of x plus the integral between 0 and t of sigma prime u xu of x ds of xu of x dv. Okay, so I have this one. If I denote by notation, if I denote by wt ds of xt of x, what I have proved with my previous computation is that for t greater than s, wt fulfill a particular stochastic differential equation that is the following one. I have that d of wt is equal to what? So I use this one here to say that d of wt is equal to what? It is equal to b prime of t xt of small x wt dt plus this term here that gives me sigma prime of t xt of small x wt dbt. So for t greater than s, I obtain this one. And I have also that for t equal to s, what I obtain for t equal to s in my equation here. For t equal to s, okay, so if I replace t by s here, I have the following. I know that ds of xu is equal to 0 if s is strictly greater than u. So if you integrate here with a u that is between 0 and s, this term is equal to 0. So let's write it here. So I copy. I have this one. But I have that WU is equal to 0 for U pretty greater than S. Okay? So excuse me, so WU is ds, so I have done a little mistake here. It's equal to 0 for, okay, so for S greater than E. And that's why if I take U between 0 and S, okay, except for small s, I have all these quantities that are equal to 0. And so from this one, I can deduce that Ws is equal to sigma s xs, because from this argument, I have this one that is equal to 0, and this one that is equal to 0. So if I summarize what I have obtained, okay, so if I summarize what I have obtained, I have obtained that if I denote by Wt ds of xt small x, I have that dWt is equal to b prime t xtx wt dt plus sigma prime t xtx wt dt for t greater than s, and that Ws is equal to sigma s xs of x. Okay, so I see that W for t greater than s fulfill this stochastic differential equation. Okay, but in fact, I already know this stochastic differential equation. If I come back to the definition of the first variation process we have seen together, that is here, I see that the stochastic differential equation fulfilled by W is exactly the one that is fulfilled by the first variation process, exactly the same. So I can write that for t greater than s, Wt and ytx fulfills the same stochastic differential equation. They fulfill the same stochastic differential equation. So from what you know from the semester one, so from semester one, there exists lambda, that is a random variable, such that, in fact, W and Y are proportional. Okay, so there exists a lambda such that W and Y are proportional, so it's a random proportionality coefficient here. It's because, okay, when you have two processes fulfilling the same stochastic differential equation, okay, they are equal to up to a multiplicative constant. And if I taking t equal to s in this equality, I have that Ws is equal to lambda ysx, implying I know what is Ws. Ws is equal to sigma s xsx, so I have lambda that is equal to sigma s xsx over ys of x. And keep in mind that I have the right to divide by y because it's the first variation process, and we have seen together that this first variation process is strictly positive. Okay, so I have this. And finally, if I use this point and this point, I have this one plus this one, that gives me that Wt, that is ds of xt, is equal to lambda yt with lambda that is given by this one. So I obtain this one for t greater than s. That is exactly, this one is exactly what I want to obtain here. Okay, so you see that the value of ds of xt of small x, okay, is may be computed this way using the first variation process, because, okay, they fulfill for t greater than s the same stochastic differential equation. So they are equal up to a multiplicative constant, and using the properties of the derivative operator, I am able to fix what is this constant, okay, in terms of the coefficient sigma of the stochastic differential equation and the inverse of the first variation process at time small s. Okay? Okay, so if I am in the case of the Black-Scholes model here, so for the Black-Scholes model, keep in mind that you have sigma of s xs of x. In the case of the Black-Scholes model, that is just equal to sigma xs of x. You have, for the first variation process in the Black-Scholes case, you have just xt of x divided by x. You have ys of x, that is xs of x divided by x. If you plug these three in this basic relation, you obtain for the Black-Scholes model the value of the derivative operator that is given by this expression, okay? An expression that it is simply possible to obtain, okay, if you apply the chain rule to xt, because you know that xt is the geometric Brownian motion, okay, and in fact you can do directly the computation using the chain rule, but you have another way through proposition 8 to obtain this result. So what is nice with this proposition is that, okay, the value at time small t of any solution of regular stochastic differential equation belongs to the domain of the derivative operator, and that I have a nice formula in order to compute the derivative operator in relation with the first variation process, okay? And now it's what we are going to use in order to, to do what I want to do today, that is to be able to obtain weights, okay, for the computation of Greeks in the general domain we are going to work with today, and for particular contingent claim. And we are going to consider two types of contingent claims. The one that are, okay, basically related to classical put and call options, okay, and the one that is related to what we call ASEAN options. But we are going to see that, okay, for both situations, the idea on how to obtain the weights in order to avoid finite difference came in the computation of the Greeks, okay, is basically the same one, okay? So I have this one, and I repeat that I know that I don't have the proof of this point here, okay, because it is a little bit technical, and it will be the objective of one of the projects I will give to you, okay, as a final evaluation of this course. Okay. So let's continue. So the first case we are going to consider is the case where I want to compute the Greeks for a contingent claim that is of this form. Okay? So why I put in parentheses here actualize is that because, okay, in fact, you know that in general, okay, the price at time t equal to 0 of a contingent claim is given by the conditional expectation under Q of the actualized payoff. Okay? And I just say that in fact I can write this expression this way with an F tilde, where in F tilde I have internalized, okay, the discount factor here. So that's why here I will consider only this situation in order to not to work with this actualization, okay, that will change nothing in what we are going to do, okay, just because I don't want to write it every line, okay. So actualize means that I have done this and consider something of this form instead of considering, okay, a function of the final value of the risky asset multiplied by the discount factor, okay. So in particular, what I will do in this situation, okay, will be okay for, can have classical call option, classical put options, okay. And by independent, and I remind you that it is because here I have a contingent claim that only depends on the final value of the risky asset. That is, it doesn't depend on the whole trajectory of the asset. And what I want to do, okay, in this situation is to obtain for the delta at time t equal to 0 or the gamma at time t equal to 0. And I repeat that I do the things at time t equal to 0 in order to simplify just the computations, but they are exactly the same. I want to write, okay, the delta and the gamma this way as the expectation. So that is implicitly here the expectation under Q, the one equivalent martingale measure of the payoff multiplied by a random variable I have to determine, okay? And what I want is that this weight I obtain here is independent of small f. That is, I have the same weight for any f, in particular for any put, any call, okay? I want the same weight in order to compute the Greeks, okay? So first of all, two little technical lemma in order to simplify a little my problem, okay? So I said the following. In the lemma 5, I said that if I want to obtain this relation here that I call the relation star, okay? So it's the relation star, this one. If I want to obtain it for all small f such that this one is in L2, which is exactly what I have written here, but it is necessary and sufficient to obtain it taking only for small f something that is of class C infinity with compact support. I just remind that means class C infinity and compact support. Okay, so why I have this by? I have this by classical arguments. Okay, first of all, I see that if I have it for all this f here, the one that make f of x capital T in L2, of course, I have it for the f that are of class C infinity with compact support, because if I am of class C infinity with compact support, in particular, I am bounded, so this random variable is in L2. So the side from the top to the bottom, okay, is obvious because this set, okay, the set where f is, belongs to this one, okay, is included in the set of the f, making this one in L2. For the opposite, so I can write it, okay, that I obtain, I can write them this way, just a little here. I will write the thing this way. So here, I said that this side is obvious because if I have, I repeat, if I am of class infinity with compact support, I am bounded, and so this one is in L2. And for the other one, what can I do? I suppose that I have a result for very regular mappings, okay? I want it for less regular one, okay, but I will do it by approximation. Okay, because I know that this one is dense in L2. Okay, so I will use the density, And keep in mind that even if these one are very regular, since what I want to obtain here is completely independent on the derivative of f, okay, I will be able to extend this relation. If I have it for very regular payoff, okay, passing to the limit, I will be able to extend it for less regular one, okay. So you will see that it will be, so I won't enter in too much details here because it will be one question in most of the, the project I will give to you. Okay, so it means that if I want to prove this, in fact, according to the lemma 5, I can restrict myself to very, very regular payoff in the sense that I can restrict myself to the case where small f is of infinity with compact support. Okay? So what is the interest of working with small f of class C infinity with compact support? But it is very interesting because, okay, if I consider the price function here, so if I consider the price function Px, that is the expectation, okay, so of this one up to the actualized factor, okay, and if this one is of class C infinity with compact support, okay, but I will be able to use Lebesgue type theorem in order to study the dependence on small x of this quantity here, and I will be able to use, okay, all the Lebesgue regularity theorem, okay, in order to say that P is of class C1, and that in order to compute P prime of x here, that is just the delta at time t equal to 0 in this situation, I can just compute the derivative under the expectation. So I will have the expectation of what of the derivative with respect to x of this one. So I can use the chain rule to obtain that I have f prime of x capital T of small x multiplied by what? By the derivative of this one with respect to small x. But the derivative of x capital T with respect to small x is what I have called the first variation process at capital T. I remind you this here because y capital T of x is just the derivative of x capital T of small x with respect to. Okay, so here it's a consequence of Lebesgue plus the classical chain rule. Okay, so in the situation where my contingent claim has this form here, I can restrict myself to prove this formula for any f. I can restrict myself to the case where small f is of class C infinity with compact support using this approximation argument here. And what is more, in the case where f is very regular, that is of class C infinity with compact support, I have this expression for the delta at time t equal to 0, defined as the derivative of the price function with respect to the initial condition. The way to play is just to use, okay, classically the derivation under the integral sign or under the expectation and the classical chain rule. And now I will be able to state the first result concerning the way to obtain a weight. It will be first result concerning how to obtain a weight for the expression of delta in the case where the contingent claim has this form. As I have seen previously, I can restrict myself in order to do this to the case where f is very regular, that is of class C infinity with compact support. So you have, so I can erase this slide here, and I have this proposition that we are going to prove together. So what is the meaning of this proposition? This proposition tells you the following. So keep in mind that I want to obtain for the delta, I want to put it on the form here of the expectation of the payoff multiplied by pi, okay, the weight. And I said that I will be able to take the weight of the squared integral of W, where W is in the domain of the squared integral, if and only if W fulfills this condition. Okay, so in order to be able to take a weight of this form that will work for the delta in the case of a path independent contingent claim, it will be necessary and sufficient to check that I have this equality between this conditional expectation, okay, okay, where W is inside this expression. Okay, so we are going to do the proof. So as you will see, okay, it seems to be complicated, but in fact it's not. Okay, so I will do the proof. So I have an if and only if to prove. Okay, so I have this one, this implication, and the other one to prove, and we are going to do the proof of this one. And you will see that it will be a basic consequence of what I have done before. Okay, so suppose that you are in this situation. That is, okay, I suppose that for all f of class infinity with compact support here, I suppose that delta 0 of x is given by this expression. Okay, where I know that since f is very regular, I have here, so from the regularity of f, I have this one that is in the domain of the derivative operator, and so f is of class C1 and Lipschitz, so I have someone here that belongs to D by proposition 2. Okay, so let's come back to what I have seen previously. So let's come back to what I have done in this course here. And in this course concerning the square integral, we have seen the following. We have seen that I have this relation here. So if you have u that is in the domain of the square integral, and if you have f that is in the domain of the derivative operator, then the expectation of f multiplied by the square integral, that is exactly the type of term that I have in what I want to compute, may be written expressing this quantity using, okay, the derivative operator of capital F this way. It is just the expectation of the scalar product in L2 of 0 capital T of the derivative operator of F and U, the process of interest here. So if I come back to my point, what I have here, I have exactly what I need. I have here the expectation of someone that is in the domain of the derivative operator multiplied by a squared integral. So by the definition of delta, I can say that this expression is equal to the expectation of the integral between 0 and capital T of dt of f x capital T x wt dt. It's by the definition of delta. That is the adjoint operator of D, okay, the derivative operator in the Malliavin sense, okay, in the good spaces. Okay, so I have this one. What can I use now? I have here someone that is C1 and Lipschitz. So I can use the chain rule for the derivative operator in the Malliavin sense, that is the proposition 2. And I can write that here I have the expectation of what? The integral between 0 and capital T. So I apply the chain rule to this term, f prime x capital T small x dt of x capital T small x wt dt. And what is nice is that here I have something that is independent on small t, so I can remove it from the integral here. So I have something like this here. Okay, so let's continue. I have the expectation, so I can remove this one from the integral. And I have the integral of what? Of the derivative of this one multiplied by Wt. So I have Wt dt here. And I have the derivative of this one. But keep in mind that the derivative of this one, I have already computed it because x capital T is the value at capital T of the solution of a stochastic differential equation with the good hypothesis. So if I come back to what I have proved, that is this one, no, excuse me, it's this one here. I have an expression for dt of x capital T, okay? And I can use this expression. So from proposition 8, here, I have the fact that dt of x capital T is equal to what? Is equal to y capital T of x, y small t small x minus 1, sigma of t x t small x. And I don't have the indicator function because here, okay, I know that small t belongs to 0 capital T, so small t is always less than capital T, so the indicator function in the usual, so here I use that this one is equal to this one by proposition 8, okay? So I have this one. So I can simplify a little, and I obtain that my delta 0 of x is equal to what? It is equal to the expectation of f prime of x capital T small x multiplied by what? So here I have something that is independent of small t. So I have y capital T small x integral between 0 and capital T sigma of t xt of small x divided by yt small x wt dt. So I have this. Okay, so delta 0 is equal to this expression where you see that the expression I have here is exactly the expression you have here. Okay, so how to conclude? But I can conclude using the previous lemma. In the lemma 6, I have proved that for all f of class C infinity with compact support, delta 0 is given by this expression. Okay, so by lemma 6, I can use this equality here. I can use this equality. So this one is equal by lemma 6 is equal to the expectation of f prime of x capital X small x, y capital T small x. And in fact, it's finished. Why it's finished? Because I have the equality between these two expressions, an equality that is true for all f of class C infinity with compact support. And from the definition of the conditional expectation, the fact that I have this equality for any f of class C infinity with compact support means that the conditional expectation of this quantity with respect to x capital T of small x has to be equal to the conditional expectation of this one given x capital T of small x. So this one implies exactly what I want. Okay, so you see that the computation is in fact here very short, and the proof of one side of the proposition is very short. I start from the delta this way. I use the definition of the squared integral. I use the chain rule in order to compute this derivative. Then I use by proposition 8 what is the derivative of a solution of a stochastic differential equation. I obtain this equality here, and from the lemma 6 I remark that this expression is none other than this one. So the conditional expectation of this term and this term has to be equal with respect to the sigma algebra generated by this random variable here. Exactly what I have here. Okay, so it's to prove from the top to the bottom. Okay. In order to do the converse, but in fact, in order to do the converse, I have to do nothing. Because okay, you have the proof here. If you want to prove from this one, but you start from the end and write everything to the beginning. Okay, so I repeat that I have done the proof of the top, supposing the top to prove that I have the bottom expression here. If you want to do the converse, you start from this one, so meaning that you will have this one, and then you continue the computation to obtain at the end exactly what I have at the beginning. Okay, so in order to obtain this one, so to do the reasoning from the bottom to the top. Okay, I have this one. Okay, so I have done the proof of proposition 9 here, and you see that only very basic properties concerning what I have done previously are used in order to do the job. Okay. So I have this one, so excuse me, so what is this? I have maybe, what is this one? Okay, it's the one I want, so I will just erase this one that I don't need. I have this one, okay, I will erase it. And I have this one. So here it's just a statement of the proposition. Okay, so the idea here is to say the following. Okay, I have a necessary and sufficient condition in order, okay, so keep in mind that I am in the case where my contingent claim has this form, okay, I am in the case where I am interested in the delta, and I have in this situation, okay, a necessary and sufficient condition in order to obtain the weight here for the delta and this kind of contingent claims, okay, this necessary and sufficient condition in order to obtain the weight as the square integral of someone has to fulfill this condition. Okay, so now we are going to see how to use this proposition in practice and concretely, okay? So it means that if I want to obtain this, I have to find the W that solves this equality. And I have an equality between conditional expectation. And the first natural thing I can see is to say, okay, if I want to equalize between these two conditional expectation, I can see if it is possible to find a W such that this one, what I have inside the conditional expectation, is in fact equal to this one. And in fact, I say that it is possible taking this natural candidate here. Okay, so let's have a look on this natural candidate and prove that it works, okay, in the statement of proposition 9. So suppose that you plug W this way. So what is W? W is equal to A multiplied by Y divided by sigma, where A is a mapping only depending on the time, such that the integral between 0 and capital T of AT dt is equal to 1. Why not? Okay, and I say that if I plug W inside this expression, it works. So the first thing I have to remark is that if I want to apply my proposition, I need to prove that W is in the domain of delta. So here, Wt is equal to AT Yt of x over sigma T xt. And keep in mind that I know that the absolute value of sigma is greater than epsilon. Okay, so in fact, I can say that this term here belongs to L2 prog of omega times 0 capital T. Why? Because this process is progressively measurable. This one is progressively measurable. This one is a mapping, so no problem. I know that this one is in L2 prog, okay, and I know that 1 over sigma is bounded. Okay, so everything, this product here is in L2 prog, and I know that L2 prog is included in the domain of delta. Okay, so I have a W here that belongs to the domain of delta, condition that is mandatory if I want to apply my proposition 9. And now it remains to prove that if I plug inside this expression W this way, I obtain exactly what I want. So let's do it, okay? So if I compute y capital T x integral between 0 and capital T sigma of t xt of x wt over yt of x dt, what I obtain. So my wt is given by this expression. So I plug this one, I will plug it here to obtain what? But the sigma will simplify, the y will simplify, and it will remain that I have y capital T of small x integral between 0 and capital T of what? Of a of t dt that is equal to y capital T small x. So I have that this expression in yellow here is equal to this one, and so that I have this condition that is fulfilled. And so in this situation, to find the weight, I will just have to compute the squared integral of this one. I will have to compute the squared integral. So, okay, so natural weight that is delta of W, okay, for the expression of the delta in this kind of thing for this content. Okay, so I have okay, so I have a natural candidate that I will be able to compute in practice. Okay, I have this, and also keep in mind that in this situation, W belongs to L2 prog, and so in this particular situation, delta of W here is just the stochastic integral, because I know that the squared and the stochastic integral coincide, okay, when W is in L2 prog. Okay, so we are going to see what happened in the case of the Black-Scholes model. So I would just do this here. I will see what happened, okay, for Black-Scholes. So in the Black-Scholes case, okay, what I have? I remind you that I have yt of x that is equal to xt of x divided by x. I have sigma t xt of x that is equal to sigma xt of x. So wt in this situation is equal to what? To at y, that is this one, so it will be at over x sigma. So if I want to be able to do a concrete computation, okay, I will need to find, okay, a particular a. And I take, so I need to find a mapping such that the integral between 0 and capital T is equal to 1. I take a that is equal to 1 over capital T. Because if I take this mapping constant to 1 over capital T, this condition is fulfilled. The integral will be equal to 1. Okay, so I have my Wt here, that is 1 over x sigma capital T. And so delta of W in this situation is equal to what? So by linearity, it's equal to this one. And I know that 1 being progressively measurable, here, this is equal to the stochastic integral of 1 over x sigma capital T. And if you remark what I have obtained here, the weight I obtain for the delta in the case of a payoff of this form is given by this one. And come back to what I have proved, okay, in what? In a proposition that I have proved, okay, during the first sessions. So where I am, excuse me, find it. Two, 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 two. This one, yeah. So in the proposition that I have proved, okay, in the first session, the delta in the case of such a payoff, okay, was given by this expression. And here, if you take this weight at time t equal to 0, you have b capital T over x sigma capital T. So it's the slide 66 of the first slides I have given to you at the introductory part of the course. You see that the weight you obtain here is exactly the weight I obtained in my computation here using the proposition 8, the proposition 9, the one I obtained here. Okay, so the same weight as in the introduction. Okay, so this is the job for the delta. Let's do the job for the gamma. For the gamma, I have this proposition. Okay, so it is more or less of the same types, but keep in mind that the gamma is the derivative of the delta. Okay, so gamma being the derivative of the delta, we are going to see that in fact the proposition involving the gamma, it's someone that will take into account what happened for the delta. Okay, so I said the following. I said that if for the gamma I want to obtain the gamma as the form of the expectation under Q of the payoff multiplied by a weight, so I am always in this situation. I have this contingent clause once again. So I want for the gamma, my classical expression I want to obtain, and I said that I will obtain a weight of the form delta of W gamma, okay, so where W gamma belongs to the domain of the scored integral, if and only if the conditional expectation of delta W gamma is equal to the conditional expectation of this form here, delta of W delta, delta W delta plus the derivative with respect to x of W delta, where the W delta is an element of the domain of delta such that this condition is fulfilled, okay? So it means that here, the condition that is fulfilled here, it's the one related to the delta. So I see that if I want a result concerning the gamma, I have inside a condition involving what happened for the delta. It's that natural because I repeat that the gamma is the second derivative of the price, that is the first derivative of the delta, okay? So I won't do the proof of this proposition because it will be the objective of one of the projects, okay? One question of one of the projects I will give you as a final evaluation, but what I want to do, okay, is just to say that, okay, I want to see what happened in the case of Black-Scholes. Use of proposition 10 in Black-Scholes. Okay, so if I want to use this, I need to find such a W delta here. But I have one. I have one from the previous slide. Okay, in the previous slide, you have one W for the delta. The W is given by 1 over x sigma capital T. Okay, so I continue with what I want to do. I am here. Yeah. So from the previous slide, I can take W delta equal to 1 over x sigma capital T. Okay? I can take this one because I know that it works. Okay, so now let's compute this expression here. In this case, so here, W delta W delta plus d W delta dx is given by what? I plug inside. I know that I have 1 over x sigma t multiplied by the squared integral of this one, that is the squared integral of something that is progressively measurable. So I obtain b capital T x sigma t plus the derivative of this one with respect to x, that is minus 1 over x squared sigma t. Okay, so I have this one. So I obtain for this quantity, okay, I can write it this way, b capital T over x sigma capital T square minus 1 over x square sigma t. Okay, if I want to take this candidate as a possible W of gamma, okay, so I can take here W gamma equal to what I want. Because W delta dW delta plus dW delta over dx here belongs to the domain of delta. And so I can take this one to be equal to this one in order to make the equality between the condition of expectation. Keep in mind that one condition on W gamma is to be in the domain of delta. So if I want to take this one to be equal to this one, I have to check if this one fulfills this condition. And here it's the case. Why? Because here my expression, okay, is given by this one. So why this one belongs to the domain of delta? So to prove this, okay, so in fact, to say that this one belongs to the domain of delta is equivalent to say that B capital T belongs to the domain of delta. And why I have this? Because here I have a constant, I multiply by a constant, so by linearity of delta, I have no problem with this, okay? So in order to check that this one belongs to the domain of delta, I have to check that B capital T belongs to the domain of delta. But let's come back to my previous course. I have the definition of delta, and I have also checked that for elementary stochastic processes, okay, of this form, they are in the domain of delta. And what are elementary stochastic processes? They are processes that are linear combination of an element that is an elementary random variable multiplied by an element in L2 of 0 capital T. So here I can take n equal to 1. I can take f1 equal to b capital T that belongs to S, of course, because it is a stochastic integral, it's a linear integral, this one, and I take h1 equal to 1, and I obtain, in this case, u of t that will be equal to simply b capital T. Okay? So, this one belongs to the domain of delta. So, from lemma 3, so from lemma 3, b capital T belongs to the domain of delta. And if I want to compute delta of bt, I have simply to apply this formula. In the case where n equal to 1, f1 is equal to b capital T, h1 is equal to 1. So I obtain what? So it's b capital T multiplied by this one h being equal to 1, so this integral is b capital T also. So I obtain b capital T square from this expression minus, so the derivative of this one is the indicator function between 0 and capital T, h1 being 1, okay, so the derivative here is also 1. So I obtain simply here this scalar product, that is the scalar product between 1 and 1, that is capital T. So the computation of delta of b capital T here is from lemma 3 equal to this one. So I come back to my course here, and I said that, okay, from lemma 3, and what is more, I have the value of delta of bt that is equal to bt squared minus capital T. I have this one. So let's continue my computation, and at the end, so taking w delta equal to 1 over x sigma capital T, we have delta w delta w delta plus d w delta over dx that belongs to the domain of delta. So I can take, using proposition 10, w gamma equal to w delta w delta plus d w delta over dx that give me b capital T over x sigma capital T square minus 1 over x square sigma T. Okay, and from what I have said previously, if I want to compute delta of w gamma, that will give me the weight here, that will give me the good weight, I have to compute delta of this expression. So by linearity, it is delta b capital T over x sigma T square minus delta of this one that is progressively measurable. So I obtain b capital T over x square sigma T. And from the previous slide, I have seen that delta of bt is just bt square minus t over x sigma t square minus bt over x square sigma t. So it means that in the Black-Scholes model, the weight pi I can take here is given by this expression here. Okay? And what is this expression? If I come back to what I have done in the first sessions of this course, okay? So where I am here. It's this one. No, it's this one. Okay, I have a proposition concerning this. It's the one I have proved. Where is it? Something like here. No. Let's recover it. Okay, it's one of the things here. No. Here. So in the case of a contingent claim that is path independent for the Black-Scholes model, I have proved in the first session, slide C6 of the first slides I have given to you, that for gamma at time t equal to 0, I have this expression at time t equal to 0, and you see that this expression at time t equal to 0, small t equal to 0, is exactly the one I obtained with the new arguments. That is this one. Okay, so I have this. But at this stage, what I have, so it means that for path independent options, we have obtained by proposition 9 and proposition 10 the way to obtain weights for the delta and the gamma in this case, okay? The weights that are of the form the square root integral of sum 1, and I have a necessary and sufficient condition for this sum 1 to work, okay? And I have just proved you that in this situation, okay, I am able to recover the result I have obtained in the case of the Black and Scholl model, okay? But I am able to recover this, but keep in mind that I have also this result now for more general models, okay, the one that are given by my equation capital E. So even for this very simple case, the case of path independent option, I am able to use and to obtain Greeks or weights for Greeks for more general capital E, equation capital E, so for more general solutions of stochastic differential equation. Okay. Now we are going to finish the course, okay, studying another situation, the case where I have a path dependent option that is in fact an ASEAN option. So I will conclude my course. Maybe I can erase this one, yeah. So we are going to conclude the course, okay, considering, okay, contingent claims of this form, a function of the Riemann integral of the risky asset. Okay, it's what I call the path dependent option because it depends on the whole trajectory of the asset because I integrate it. Okay, it's an option average in some sense that I call an ASEAN option. Okay, and we are going to prove that in this situation I am able to do exactly the same thing that I have done previously. Okay, and what is nice even in this situation is that even in the Black and Scholl case, okay, in the Black and Scholl case for ASEAN option for the moment I have nothing. And even in the Black and Scholl case, I will be able to obtain weights for the delta in this situation, okay? Things that I don't have obtained for the first station. Okay, so I will just do a 5-minute break, okay? And I will come back to finish the course in 2 minutes.